Hey guys, welcome to the second lecture on magnetic circuits. This will be the second part of a two-part series, and we will be talking about the pH curve, core losses, permanent magnet circuits, as well as a brief summary of both. We'll be discussing the pH curve in this portion. So what the pH curve really talks about is the behavior of a magnetic material when an external magnetizing force is applied to it. So we can produce a magnetizing force H with the help of an ion. We've all studied it by the Ampere's circuital law. We could produce an H, and when there is a particular body, a magnetic body, or a magnetic material that's placed within this magnetizing force H, it's going to cause a B to be induced inside, or it's going to cause a B to be produced inside of the body with relation to the mu r of the body. So the formula is B by mu equal H. So the B will be equal to its permeability times the magnetizing force that we're going to apply to it. So let's say some B is produced, and that would depend on the mu I, would depend on the properties of the body, but let's just say some B is produced. Now when we take off this H, the H is now 0. Some portion of the B would still remain. So it may not be exactly the same, maybe a bit of it is taken away, and this B still remains. Now how do we get rid of this B? Right, we've got to apply field in the opposite direction. So maybe with the application of a little bit of H in the opposite direction, it's taken away a B a little bit more, and with the application of a bit more, it's taken the B away completely, and we apply a bit more of H, maybe there's a B produced in the opposite direction, right? And now, yeah, let's say B is produced in the opposite direction. Again, we take off the H, the B is gonna reduce, not completely, but a portion of it's gonna reduce, but it's in the opposite direction now. And now if we put the H back, again the B is going to diminish further and further, and then if we increase it even further, the B is going to go back to the initial direction. Now this can be plotted on a graph. Right, let me just this is B and H. H is on the x-axis, B is on the y-axis. Now H is what we're applying to the body, and B is what's happening inside the body. So you could say H is cause and B is effect. H is the input, B is the output. Well, we have this portion, right? I produces H, produces B equals or produces flux, right? So we have this was discussed in the Ampere's circuital theorem. This portion is what we're discussing right now. So what happens is, initially the body has no magnetization within it, and we haven't applied any magnetizing force, so it's exactly at 0 actually. And then as we increase the H, the B inside increases almost linearly until it saturates, right? So it has a limit. After a point, if we increase the H further, the B is not going to increase as much, and this is the point of saturation, or the region of saturation. This is the linear region, right? And then when we talked about reversing the direction of H, let's say H is now 0, so as it falls to 0, it's a bit of an error. Yep. Okay, when it falls to 0, it reduces and gets to a particular point. And when we apply an H in the opposite direction, it reduces further until it gets to this point. Now it's completely demagnetized. There is no B within the body. It does not have any magnetic. It doesn't, let's say, attract or repel another permanent magnet. Now if we apply H even more in the opposite direction, a B in the opposite direction is now produced inside the body until it saturates. This is linear and it saturates, And then now if we take off the h, where h is now 0, the b reduces in the opposite direction, but it reduces from this point to this point. And then if we apply an h again in the opposite direction, we get back the b to a particular point. Now, this may not be the same point. Now, if we repeat the cycle again, right, if we are going to apply it opposite, it necessarily doesn't have to be at the same points. It won't be on the same points. And this is what we call hysteresis, where the behavior of the body is dependent on its history. So let's see, it may flow this way, like that. Maybe it might act this way in the third cycle. It's going to follow a similar shape, but it won't exactly be the same. You can't exactly say that, okay, at first this was the point, but the second time it's this is the point. It doesn't, this is the way it is. So this is the BH curve. And we're discussing this here because we're considering an AC current source that's producing this magnetizing force H. So there's cycles of it increasing and decreasing back and forth, right? Now, there is some loss of power due to this BH curve, due to this hysteresis curve. If we have a thin BH curve, maybe this one, it's going to dissipate, let's say, lesser energy. It's going to consume less power as compared to one that has a thicker BH curve. So the area of the BH curve would dictate the losses occurred in this magnetization and demagnetization process. Now here we'll be discussing the losses that occur during this BH curve, or this magnetization demagnetization process of a particular magnetic material. And why must we learn this, right? So first off, when we have an electric machine where you make use of magnetic circuits, where you make use of magnetism, like a transformer or a motor, you would have multitudes of losses, or well, just some categories of losses. So you inject some power into the machine, and some of it is obviously lost in the wire, in the copper windings, as I square R losses. Of course, it's inevitable. If there's resistance, there's going to be losses by resistance. Some of it, or some of the energy that we're going to apply into the machine, is lost within the core, because we're magnetizing it and then magnetizing it in the opposite direction, because we're dealing with AC. So the currents in this manner, so in this cycle it's going to magnetize, then it's going to go to 0, and then it's going to demagnetize it, and then magnetize it in the opposite direction, and so on. So it's a complete BH curve again and again and again. So there's losses due to that, right? So I'm just going to write hysteresis losses. And then there's another component, which is eddy current losses, where eddy currents are induced within the bulk of the core, and we could, well, deal with that or get rid of that using laminations. I'll come to that just after this. Now, to quantify the losses we'll be dealing with, we need to consider how much of energy is transferred. Energy transfer into the core during this process. So we're going to consider one cycle of AC here, just one cycle. One cycle of current. Now, we know that energy or work is the integral of power with respect to time, going T1 to T2. And we know that power is E times I, or voltage times current, right? In this case, I'm just going to write E for induced EMF. And from Faraday's law, we know that the induced EMF in magnetism is mostly dN phi over dt. It's actually negative, but I'm just going to omit the signs and just go with the magnitude. So we have n d phi over dt, because n is a constant, don't forget the integral, and we have dt. So we could just get rid of these dt's and just write it down as n. Oh, well, this is EMF, and don't forget the current. I almost forgot. So ni dt, oh sorry, d phi because I could just cancel out the dt's. Or not exactly cancel out, but you get the idea. So we could write down from Ampere's circular theorem, we could write down that HL equals Ni. So we could write down equals a direct substitution. So HL d phi, and since we know that phi equals Ba, where phi is magnetic flux and B is magnetic flux density, we have HL A dB. Now A is taken out because A is a constant. The area of the loop is not changing in this particular scenario. So we're going to take these values out, A, L, H. We'll just take out AL and put it this way. Now A and L is the area and the length of the core. So if we have the area times the length, it gives us volume, right? I'm sorry. L times A gives us volume. This is a cylinder, but for most objects it gives us the volume. So we could just write V of the core times H dB integral. So this is the amount of power that is, the amount of energy that's transferred during one cycle. And of course you could put the limits B1 and B2. So well, this is energy and this is volume. So energy by volume kind of gives us energy density. So you could technically say this is energy density. So W of the core is V core times energy density. And I'm just going to erase the top. The energy density is integral H dB. Yeah, and also the power that's lost in the core can be found using energy times, well, divided by time period here, because we're considering one cycle, and 1 over time period is frequency. So you could technically write W core times the frequency of the current that we're applying here. So in total it would give us V core times the energy density times frequency, and that is the total power that's lost due to hysteresis. And yes, the W subscript H denotes the energy density, so I'm just going to put that in the corner. So yeah, that's the losses. In the previous equations we had the power loss as energy density times the frequency times the volume. Now that doesn't really say a lot unless the values of H and P are given, unless we could see the hysteresis loop. It's not a one size fits all. We can't, and since it's only for one cycle, so we have to resort to experimental formula here, because it's not a linear function and it also follows hysteresis. It's not the same all the time. So we know that the loss is proportionate or dependent on the area of the BH curve. Of course, if we have a material made of hard iron or a hard material and a material made of soft iron or some soft material, of course the losses are going to be much higher here. And this is the retentivity or the remanence, where if the H is taken off, how much is remaining? So retentivity. And coercivity is this point where how much do you need to coerce it to demagnetize in the opposite direction. And these two values are much smaller for a soft material. Now, okay, coming to the point, the area, experimentally speaking, the area of the BH curve is given by the formula K P max to the power n. Now K is a constant that depends on the material, and n is also a constant that depends on the material. And B max is the maximum induced flux density within the material. Now in every cycle, you could see it saturates at a point, so that saturating point of P, that is in this point, this is the highest point. So we take this one as B max. N is actually called the Steinmetz exponent. It is around the range of 1.6 to 2, but it's just an approximate. It varies for different materials. And the power that's lost due to hysteresis is just the area times the frequency. That's the equation for power that we found out using experimental means. The other part of the losses that we have to discuss is the eddy current losses that occurs in the core. So when an AC current is applied to a magnetic core, it produces currents in this fashion, like an eddy. And this is much smaller when the area of the eddy current is much smaller when you laminate it. So if you make it even smaller, it becomes even smaller. So that's why the cores of transformers are basically sheets that are laminated. That is to avoid the eddy current losses. Now the equation for the power loss due to eddy current is again similar to the previous one. It's the eddy current constant times the B max to the power 2 times frequency to the power 2. The only difference from the hysteresis is that it's proportional to frequency squared, while hysteresis is proportional to just frequency. And also it has a Steinmetz constant, the hysteresis one, while in this case B max is just squared. That's the only difference. So total core loss would be eddy current losses plus hysteresis losses, and the KE varies. So for a smaller sheets that are laminated together, the value of KE is much smaller than it would be for a large bulk of the core. And also I think the thickness of the sheets used are maybe 0.3 to 0.5 mm. Now coming to an experimental setup with a permanent magnet. Well, not an experiment, this is an apparatus where we have a C shape made of soft iron and then a piece of hard iron placed, and we're supplying current through a loop wrapped around it. Now, what would happen to the hard iron? Well, starting off, we know that we're at point 0 and it increases linearly, that is, the B increases linearly with H and then it saturates. And then as we take the H off, it falls a little to the point of retentivity, or this is the residual magnetic field within the body. Now it's technically a permanent magnet. It's magnetized. Now if we, take off the hard iron, I think it could interact with other magnets. So it's technically a permanent magnet. It doesn't always have to be, and something you find on the ground or something like a natural magnet. It doesn't have to be a natural magnet. We could magnetize materials and it's, as long as it's reasonably permanent, it has a reasonable magnetic field, we can call it a permanent magnet. Now, what happens if we reverse the H, right? Of course, it goes down all the way to 0 and then more. But what if we don't go all the way down, or we reduce the H, or increase it in the opposite direction all the way until B becomes 0? What if we take it here and we stop? What would happen? Well, what would happen is, it would go back to this point where H is 0, but it would move in this fashion. It has actually increased a little. And then if we bring back, so I'm just going to draw some arrows so we can be clear. It goes this way. And when we increase the H in the opposite direction again, it follows this way. So if we do the same thing at another point, we get the same result. And these loops are called minor loops. And these minor loops would represent what would happen if we just cut off the external field. And you could see the slope of this line that's joining these 2 points would be the same as this line. So the slopes are same. That means these 2 lines are parallel, and these lines are called recoil lines, technically, because it's recoiling, right? And if we increase the h in the opposite direction even further, it's going to follow another recoil line, but they're all parallel. So technically, if we want to bring back our object to zero magnetization, right, with a completely removed h, we have to technically go beyond b is equal to 0. So we have to magnetize it in the opposite direction so that we could get a line of the same slope here. So I think I drew that wrong. Let's see, it's this way. So maybe like that. Well, my drawing's not exactly out of exactly to scale, but you get the idea. So we need to reach to this point for it to return back to a point with 0b, and when no h is supplied, right? And if we do it back, it goes back again in this manner, in another minor loop. So these are called minor loops. They have a locus of the BH curve, and the blue are recoil lines, and they're all parallel. So parallel recoil lines. And there we go. Now we'll be talking about another topic where, let's say we make a gap in this apparatus. So we have an air gap here, and it's of length LG, and this core is of the length LC. Now we'll also take off the supply of current, so no more current supply is being provided. It's just the already magnetized core. And from Ampere's law, we can write down that Ni is equal to HCLC plus HGLG. Or in this case, I'm just going to use M for permanent magnet, and Ni is 0, so we could have HM LM equals negative HGLG. And yeah, we could just rewrite this off the form. HM is equal to negative Hg times Lg over Lm. Now for the continuity of flux, so the flux that's going in is the same that's going in all the way. It's like current to a magnetic circuit. Current to an electric circuit is flux to a magnetic circuit. So for the sake of continuity of the flux, we could have flux is equal to, say, BM AM is equal to, is equal to PGAG, where this is the flux density to the air gap and the area of the air gap. And again, we're neglecting fringing. So we could write it down as BM is equal to PG, just write down AG upon AM times BG. And BG can be written as AM times mu naught into Hg, and this would make sense because mu naught is the permeability of free space. Now we could go down further and write Ag Am mu naught, and we could substitute the value of Hg from here to give us negative Hm Lm over Lg. And I'm just gonna erase the top for more space, and this was from that equation that I just erased. So this gives me Bm equals negative mu naught Ag Lm over Am Lg times Hm, and I could just write it down as M into Hm. And this is technically a slope. So let's take a BH curve on this end. So this is after it's magnetized. So this is H, PM, HM. So at a particular point, so when we had, let's say, the minor loop where we stopped the value of H and then it returned back, we could have a particular value M, and this is the shear line. This is the slope over here. As you can see, it's of negative slope, and the slope of this line is M, that is given by this block right here, and this is the shear line. So to decide a particular value of the B, you could find the value of H to supply by using this particular equation. So yeah, that is the shear line, the M. Now it is also possible to find the volume of the permanent magnet used. Now we're not going to consider the soft iron, we're just going to consider the air gap and the hard iron. So let's see, the volume of the permanent magnet is area of the permanent magnet times the length of the permanent magnet. Well, Lm. That makes sense. Now we have the Ampere's law, and the Ampere's law states that Ni equals HClC, or in this case HM Lm plus HGLG. So we have Lm equals negative HGLG upon HM, and we're not going to use the negative because we're just going to substitute back into the volume formula, and volume can't be negative, so we're just going to go with the modulus there. And for finding AM, we have the continuity of flux formula. So we have PM AM equals BG AG. Oh yeah, and in this case, Ni is equal to 0. That's why we've got this equation, if it wasn't obvious. Now AM is BG AG times PM. We substitute these equations back. We have BG AG upon BM times HGLG upon HM. Now we know that Hg is equal to Bg upon mu naught. So here we could just use this formula to give us Bg squared upon mu naught Ag Lg upon Bm Hm. And AGLG gives us the volume of the air gap, so we could use it as Bg squared upon mu naught Bm Hm times Bg equals Vm. And this is how you find the volume of the permanent magnet. So this is the final part of our lecture. Well, the lecture is actually over, but this section would summarize what we learned in the past two lectures. That is this one and the previous. Well, just a basic summary of magnetic circuits. So first we'll start off with the Ampere's circular theorem. Well, the Ampere's circular theorem states that a current carrying conductor would produce a magnetizing force surrounding it, or a magnetizing field intensity, and that is represented by H. So the I produces an H, and this is irrespective of the medium in which the conductor is immersed in. And this H magnetizes or induces a flux density in the medium that it is surrounding or surrounded by, and that is the B, that's the flux density. And this is the Ampere's circular theorem, where it connects the current to the magnetizing force. The H and B are related to a hysteresis curve, in which the x-axis is the H, the y-axis is the B, and the curves, they are dependent on the material's history, so it doesn't follow the same curve every time. It may take a different shape in the next cycle of current, and so on. And this, since the flux density is given by B, the total flux is an integral of flux density over area, or If both B and A are constant, it's just B times area, right there, just like that. We would now be discussing reluctance. And reluctance is the magnetic analog of resistance in electrical circuits. So these are the analogs. For voltage, we have Ni, that is the magnetomotive force, MMA, and this, in a magnetic circuit, this acts as the, well, similar to the voltage source in an electrical circuit. The resistance is analogous to the reluctance, which opposes the flow, well, resistance opposes the flow of current, and the reluctance opposes the flow of the magnetic flux. And magnetic flux is what flows into the magnetic circuit, similar to current in an electrical circuit. Moving on to inductance. Inductance is denoted by N phi over I, and that's also equal to N square upon reluctance. And inductance is inversely proportional to reluctance. Now, inductance is defined as the amount of flux that is produced in a magnetic substance per given amount of current. Now, coming to converting a magnetical apparatus such as this into a circuit. Now, this is a wire that's wrapped around in this fashion with N1 number of loops. The same wire goes around, wraps here with N2 number of loops. Now, we could figure, and assuming that the core has a reluctance of 0, the only resistance or reluctance we have to consider is the reluctance caused by the air gap. Now, with the right hand thumb rule, we could figure out that the magnetic flux is flowing in this direction to this particular source, and in this case the current is moving this way, coming up here, and according to the loop, let's see, it's producing a magnetic flux that is in this direction. So when we rewrite it, it has two sources and it has a reluctance in the middle, and the sources are oriented this way. Since the first flows this way, the second goes in the opposite direction. This is N1 and 1I, and this is N2I, and this is the reluctance. Now you could just simplify it just like you would for a standard electrical circuit, and you could get the required answer. Moving on to Faraday's law or Lenz's law. This is widely used in transformers. It states that when a particular conductor, when the magnetic field that is associated with a particular conductor changes, a current is induced in the conductor to oppose this change of flux, and that is given by the equation EMF is equal to the negative derivative of N phi. N is taken out because it is a constant, and the negative signifies that it is done to oppose the change, but in magnitude it's just N d phi over dt. The RMS value of the induced EMF is 4.44 times the number of turns of the loop times the frequency times the maximum value of magnetic flux. When discussing the losses in an electrical machine, we first have to consider the following. So the power that's injected in, and then there's power that is received on the outside. This is the useful power. Now, the losses are mainly of two parts. One is the copper losses in the windings, that is I square R losses, and the core losses, that is in the core. And one of it is hysteresis losses, and the other one is eddy current losses. Now, hysteresis losses is the transfer of energy from, of course, the input power into, let's say, power that is lost in magnetizing and demagnetizing the core for every cycle, and that ends up just heating the core. Eddy current losses are basically due to induced eddy currents within the core, which end up, well, producing heat based on the I square R formula. And these are the two losses that occur in the core, and together with the copper losses, it forms the total losses within an electrical machine. Now, coming to the last part of magnetizing and demagnetizing a permanent magnet. When a permanent magnet is first magnetized and then the H is cut down to 0, this is the point of remanence, and when we reduce the H or increase it in the opposite direction and then cut off the H, it follows back in a minor loop, and then when we increase the H in the opposite direction again, it goes back, and this process repeats no matter where on this curve we do it. And each minor loop has a shear line, which is the line connecting these 2 points, that is this particular point and this particular point, and the slope of these shear lines are always the same, which means that they're always parallel. So to completely demagnetize a permanent magnet, we have to, let's say, bring down the B to less than 0 at a particular point, so that we could just bring it back to 0 based on the slope. And the shear line or the slope of the BH curve can be found out using this equation, and this particular slope is the slope of the shear line, and the volume of the permanent magnet can be found out using this formula, that is Bg square times volume of the air gap divided by mu naught Pm times Hn. Now this concludes the summary of the 2 lectures. So yeah, just let me know if you have any questions in the comments, and I'll try to answer them to the best of my knowledge. Thank you.